All right, welcome to The Explainer. Today, we're diving deep, right under the hood of a language that might just be the engine for artificial general intelligence. We are talking about meta, and specifically the part that makes it all go, meta dynamics. To really wrap your head around what makes meta tick, we have to start with a pretty huge question. How do you even begin to write the laws of a universe? Or really, the laws of any system that changes over time? Think about it. Physics, biology, the stock market, you name it. Turns out, any of those dynamic systems can pretty much be boiled down to just two things. First, there's the state. That's just a snapshot of everything at one specific moment. It's the what. And second, you've got the laws of motion. These are the rules that describe how the system gets from that one state to the very next one. Okay, so let's pull this idea into the world of computers. In computer science, we have a special name for those laws of motion. We call them rewrite rules. And this is where things get really interesting, because we're basically talking about code that can rewrite itself. So, what on earth is a rewrite rule? Well, it's pretty simple at its core. It's just a formal instruction that says, take this piece of data, this expression, and transform it, or rewrite it, into this other thing. It sounds basic, but this is literally the foundation of all computation. Just think of it like this. A plus B becomes C. That transformation, that's a rewrite rule in action. It's the engine of change. And this one simple idea is so powerful that it's the bedrock for everything, from the oldest theories of computation right up to the super complex systems we're building today. So how does Meta actually put these powerful rules to work? Well, let's take a little tour inside what we'll call the Meta workshop. You can think of it as a 4-step computational assembly line, running on a really unique kind of machine. So in this workshop, you've got 4 main stations. First is the input dock. That's where all the new tasks and problems arrive. Next, they go to the knowledge blueprints, which is like a huge library of all the facts and rules the system already knows. The third stop is the workspace bench. This is where the real work happens, where things get transformed. And finally, you have output shipping, where the finished results get sent out. Let's actually follow a single task to see how it works. Let's say a query comes in. First, it arrives at the input dock. Right away, the system scans through its knowledge base, its library of blueprints, looking for a match. If it finds a rule that fits, boom, that match gets moved over to the workspace bench to get processed. It's a really clean, logical flow. But here's the kicker, the thing that makes Meta so incredibly dynamic. The system isn't static. Some rules, like one called Adatom, can actually go back and change the knowledge base, that library of blueprints, while the whole thing is running. It's literally learning and updating its own instruction manual on the fly. Okay, but all that power comes with a pretty big risk, right? What happens if our workshop gets a task that it can never actually finish? How do you stop a computational runaway, an infinite loop that just eats up every resource in sight? There's a name for this, divergent computation, and it is a massive danger. In a normal program, it's just a bug. But in a huge, decentralized network, which is exactly what Meta is for, it's a complete catastrophe. It could bring the entire system crashing down. So how does Meta fix this? The solution is just incredibly elegant. It puts all of its computation on a strict budget. It creates this kind of digital currency called effort objects, or EOs for short. Every single rewrite rule has a cost, and the system can only do the work if it has enough EOs to pay for it. And this isn't just some abstract concept. Nope. Every single operation has a specific price tag. For instance, a unification step, matching a term to a rule, that might cost exactly 10 EOs. All of a sudden, computation isn't this infinite thing you can do forever. It's a finite resource that has to be managed. And the result is beautifully simple. If the budget runs out, the computation just stops. That's it. No more EOS, no more work. This idea of resource bounding is a brilliant safety net. It makes the entire system predictable and ensures that no single process can go rogue and crash the whole network. So you might be sitting there thinking, okay, why go through all this trouble? Why build such a rigid, formal, budget-based system? Well, it all comes down to the big picture, the strategic importance of doing things this way when your end goal is building something like AGI. The payoff for all this work is huge. This strict, formal approach gives you an incredibly solid foundation for AGI. For one, it means your system is correct by construction, which helps you avoid all sorts of nasty bugs and security holes right from the start. Second, it lets you do something called bisimulation, which is just a fancy way of saying you can mathematically prove that two different programs will act exactly the same. That's a massive deal for reliability. And third, having a clear, universal rulebook means tons of different teams can build tools that all work together, which is how you scale development globally. But here's the most profound benefit, the one that really hints at genuine AGI. It's a concept called meta-circular evaluation. And, put simply, it means the rules of meta can be used to rewrite the rules of meta. The system can literally look at and change its own operating instructions. I mean, let that sink in. This is a complete game changer. An AI built on this could analyze its own code, verify that its own logic is sound, and even adapt its own core programming. It's a system capable of a kind of computational self-reflection, and it can evolve itself safely because the evolution itself is governed by those same formal rewrite rules. And that brings us to the final, really provocative question. If a machine can safely and verifiably rewrite its own fundamental operating instructions, what does it become next? We're not just talking about a programming language anymore. We're talking about a platform for a new kind of self-evolving intelligence. And that is a thought to take with you.